Okay, yeah, thanks so much. It's really been a pleasure to be here all this week, and thanks for staying around to the very, very end to see this. So yeah, the title of the talk is long, but what I hope to convey to you today is that while Margie actually sagely reminded us at the end of yesterday the important governing role MHD provides for defining quasi-equilibrium structures and boundaries in planetary magnetospheres, I mean, that goes without saying, it is extremely important to understand the microscale, or what I would call in the modeling language, the subgrid phenomenon, which encapsulates the interactions between the plasma and neutrals in a lot of these near space environments of planets and planetary magnetospheres. If we need to be able to understand that subgrid dynamics if we want to understand the dynamic responsive systems, both on their mesoscale and macroscale impact. So you can have microscale interactions, which again, for the purpose of this talk, is going to be plasma-neutral interactions, which occur on a scale much smaller than any of these large-scale fluid dynamic models can directly model. But they will have an impact on the meso and possibly even the macro-scale interactions and affect the boundary layers that we see in the simulations and in the systems in general. This is a bit of an unusual talk as well. You've noticed for the last day and a half, it's pretty much been talks about Jupiter and Saturn, and then talks about unmagnetized objects, Venus, Mars, Titan. And so this is a weird one because it actually joins together two topics I'm really interested in. One is Mars, atmospheric electrodynamics, and one is Saturn. So that's an unusual pairing usually in a talk, but hopefully by the end you'll see that the bridge between these two is really something we're all fundamentally interested in, and that's the physics. So I'm going to start with Mars and spend some time talking about some of the Mars work we've been doing, and then I'll transition to Saturn in hopefully a way that's not too jolting. So the first part of this is looking at the electrodynamics of Mars ionosphere, and this is work that's actually been recently published by myself and my postdoc, Jeremy Riazet. And what we wanted to do with Mars is, of course, everyone here is quite familiar with the fact that Mars doesn't have a global magnetic field. And so we wanted to understand the coupling between the neutral atmosphere of Mars, the ionosphere, and the solar wind plasma, as well as the influence of that localized crustal magnetic field. And of course, this is of great interest to the Mars community in understanding the evolution of Mars's atmosphere. We've recently launched MAVEN, which is going to go and try and parameterize and characterize the different loss mechanisms from the solar wind and solar EUV flux interacting with Mars's atmosphere. But this has been a bit of a tricky thing to study because of the fact that it involves coupling the neutral atmosphere to the ionosphere, to the solar wind, and also incorporating those crustal magnetic fields. This has been referred to, not just by myself, although I like to use the phrase a lot, is trying to study the ignorosphere of Mars, because it really is in that region where you have to understand the neutral dynamics, the atmospheric winds, which are coupling directly to the ions and to the electrons to get out this electrodynamic current response. I really enjoyed, actually, on the first day of the meeting, that first clip from Ian Axford, where he actually starts off by defining the magnetosphere and specifically defining the inner boundary of the magnetosphere. And he says quite perfectly, actually, you know, well, some people want to put it, the inner boundary of the magnetosphere is where the ions are colliding so much with the neutral atmosphere that they become demagnetized. And then he caveats that and says, no, wait, some people want to put it even lower than that, which is where the electrons decouple. And of course, this is exactly what we want to study here with this electrodynamic model at Mars, is that region in between those two layers, which is known as the atmospheric dynamo region, or the region where the atmospheric dynamo current is generated. For the Mars atmospheric dynamo, basically the scenario is that your positive ions, which are governed by collisions, become governed by collisions with atmospheric wind-driven neutral particles. So again, that's when their collision frequency is much higher than their gyro frequency and they become demagnetized. But in this region, the electrons are still magnetized and still governed by the Lorentz force, and the differential motion between these two charged particle species is what's going to be generating these dynamo currents. So bottom I'm going to be talking about the simulation in a moment, so just to note, the simulation runs dynamically from 80 kilometers altitude, so that's really below the peak of the ionosphere at Mars, and we're trying to model between there and about 400 kilometers altitude, so it really is right the heart of this region, this area where neutral coupling to the ions and electrons becomes important. So below, about, depending on the strength of the crustal magnetic field or the local magnetic field from solar wind draping, you can end up with about below 100 or below 90 kilometers, depending, a region that is completely demagnetized in terms of the ions and the electrons, which is just to say that both of them are colliding so much with the neutral atmosphere that they can't respond normally to the electric and magnetic fields. At the top of the model, we have magnetized ions and magnetized electrons. So there are currents flowing there, of course, because you can have electric fields that are moving particles around and generating currents. But it's not a dynamo current in the way we've just gone and defined it. It really is this region in between those two, where you have demagnetized ions that are just being basically pushed around by the neutral wind, and the electrons, which are magnetized, and that's generating this ionospheric current, or this, actually I should have said not ionospheric, but this dynamo current. So that's kind of the layer cake model, if you will, that we're going to be investigating with the model. And just to put it in a more pictorial sense, I did say that the magnetic field, of course, is going to govern exactly where this dynamo region falls, because that's what's governing the gyro frequency. So you see here these are just arbitrary cases for 20 nanotesla radial strength or Z strength in our model versus 2000 nanotesla. You can see here the bounds of the dynamo region in terms of altitude. So for this weak magnetic field case, you see the blue line is the collision frequency of electrons, the red line is the collision frequency of the ions, and these dotted lines represent their gyro frequency. So where those intersect, of course, is where the dynamo region is governed, or is defined. For the stronger, and I think 2000 nanotesla, you probably won't see much stronger than that for even the strongest crustal anomalies in this altitude regime. You can see that it goes so far as to push the dynamo region down to just above 100 kilometers. So even though you have a large variability in terms of the crustal or the surface magnetic field strength, the dynamo region is pretty well confined. It's not going to go above or below really 100 up to 250 kilometers. So the model is able to encapsulate that pretty well for all scenarios. A few other details about the model is just that it's a regional model. This isn't a global model, which is what we've seen a lot of over the last couple of days. And the reason for that is, at the moment, we were really trying to focus on the physics, and this has allowed us to have very high resolution. So we're able to model regions on the order of a few hundred kilometers squared surface area, and then several hundred kilometers up into the atmosphere at a resolution of about 1 kilometer. So it really enabled us to capture a lot of these interesting dynamics. So I'm not going to walk through the equations. Most of you are familiar with them. This is a multi-fluid model, so we are keeping track of different ions and different ion species as different fluids, and an electron fluid separately from that. So it enables us to capture the dynamics of different charge to mass ratios, so carbon dioxide plus, O2 plus, O plus, through obviously conservation of mass, conservation of momentum, the equation of state, your standard MHD formulations. You'll notice, though, of course, these formulations are a bit different since it's a multi-fluid simulation. And we have included here in these colored terms, so the blue and the green terms, these are our ion-neutral elastic collisions, our inelastic collisions, so collisions resulting in effects like charge exchange, and electron collisions as well, which are going to be on the next slide. So what I'm trying to get across to you here, again, the point of the talk is that we want to see these collisional effects in action. We don't have to put any sort of resistivity, artificial or other, because the collisions are taking care of it for us. They're telling us what that resistivity is, what direction it's in, and how it's going to play out at different altitudes. Again, these are just the rest of the equations for us. We have quasi-neutrality. And again, those collisional terms actually come in to be quite important here in the generalized Ohm's law. So instead of having an A to J term, a resistivity times the current, we actually have it explicitly put here in terms of electron-ion and electron-neutral collisions. So just as a reminder, this is why part of it's so interesting. We see this as the radial magnetic field, or the BR, computed at 200 kilometers altitude for Mars. And you see, of course, there's this banded structure, this strong oscillating magnetic field structure in the southern hemisphere, where it goes from radially outward to radially inward over a scale of just a few hundred kilometers. And just so that I want to give credit where credit is due to my postdoc, Jeremy. He calls his model the Mars Multifluid Magnetohydrodynamic Model, or M4, which he was very proud of, his acronym. And the two cases that he laid out to study, and actually this is a typo, this should be 2014 because it was just accepted in January, was to look at, not as we did in our initial model, which was just these uniform vertical fields to do a proof of concept and really validate the model, but to look at the effects of interesting field morphologies, which really in the case of Mars can be represented by either a singular or a series of buried dipoles. So just to get us around the first bit of this, this is just a buried dipole. This is you could call it a cusp or buried dipole, however you prefer to call it in our simulation. And even though we drew this horizontal slab here at 100 kilometers, just a reminder that the model does go all the way down to 80 kilometers. And what you're seeing here is just mapped the radial or the Z component magnetic field strength off of the surface. So for this simple isolated dipole, which is on the order of the strength of surface dipole fields that we see scattered all over the place on Mars, what we wanted to do is see if we apply a neutral wind to our quasi-equilibrium ionosphere and atmosphere. We had run the chemistry models separately, so they're not dynamically coupled into this yet because the time scales for evolution are different. If you apply a neutral wind, so that couples to the ions, what happens to the electrons? What happens to the electron motion? What happens to the electric fields and therefore the currents that are generated in the dynamo region? And this is a really nice indicative plot. This is the electric field, and just to orient you, this is that horizontal slab, so you're looking from the top down on it, and then you can flip up to see the altitude versus X, and then this one is altitude versus Y, so you can see kind of the structures in the electric field with altitude, how they evolve and where the asymmetries are. But one of the things that was really nice is that right away we see this beautiful structure, which looks like the electric field associated with a ring current structure, even on the Earth's dipole magnetic field. And what this really represents, you can actually break down from the generalized Ohm's law all those different components. And what you find is that what you've actually generated is an E cross B current, which is a bit counterintuitive because we usually think about E cross B drift as affecting ions and neutrals, or ions and electrons the same. But if you decouple the ions out of the situation and the electrons still drift as they want to, you end up getting currents associated with that E cross B drift that play out quite nicely. And if this is just a quick animation, again, looking at the currents now, you can see this really nice E cross B drift current, and there are some vertical structures as well that evolve because, of course, you have electric fields being generated and driving the currents. You can't see it very much in here both because of the dark colors and because it's a small effect, but there is a perturbation magnetic field, of course, that evolves from this current that's changing the localized strength of the magnetic field. Not insignificantly, but not obviously dramatically significantly, because the overall structure of the field isn't changing, just the relative strength. Hence the field lines don't look like they've varied a whole lot. So that was pretty interesting, and we thought quite exciting as a novel proof of concept of being able to model this region of the atmosphere using this type of simulation. We then went and modeled oscillating magnetic fields, so radially pointing in and out magnetic fields, just by burying a series of dipoles. Again, on the order of the same strength that you see in that strongly magnetized region over the southern highlands. And again, this is just magnetic field mapped here in the 100-kilometer plane. And what we can do just to keep things moving along quickly is just show you what the current structures look like as they evolve in time. And we run these out for hundreds and hundreds of seconds. Again, that actually is a pretty reasonable amount of time to run the simulation code out to, because after that point, really, it doesn't evolve any further. You're starting it kind of artificially from stop, where you then apply the winds and watch things evolve. So you have a characteristic timescale under which the system is going to evolve. But it's actually quite nice. You end up seeing We called these the magnetic arcades for those oscillating magnetic fields of buried dipoles. And you see these really nice channels of current that form and electric fields that form because of those electric and magnetic perturbations that form in those regions as well that affect actually the vertical motion of ions in the system. Okay. So that's interesting. And now we have the very abrupt bridge jump to Saturn. And you think, well, what's really going on at Saturn? And what I really wanted to get across here is that the physics is really the same. And what we really were interested in at Saturn, there are many people looking at the ionospheric coupling, and we've done that too. We actually have implemented an ionospheric boundary reflecting the modeling work of Luke Moore et al. From 2010. But we were actually more interested in the same idea of ion-neutral collisions at Saturn, but due to the neutral cloud interaction, and solving them self-consistently. So there's two big questions, I think, in terms of radial mass transport at Saturn. The first is, what's the distributed mass and momentum loading of Saturn for Saturn's inner magnetosphere because of interactions, collisions with these neutral particles, sourced at Enceladus? And the other one is, how is newly created plasma circulated and shed in the system? And Shinja gave a really nice talk showing kind of the global MHD perspective on that. If you have source terms in the inner magnetosphere, you know, where does that go? How does it interact? And things of that nature. I'm not going to focus on that second question here because there's just not enough time to. But again, just as a reminder, you have Enceladus's icy plumes, which are sourcing the entire E-ring, both the dust and the neutrals, and that neutral cloud is quite expansive. It fills Saturn's magnetosphere with neutrals. And so, again, it's interesting because of the fact that unlike Jupiter, and this has been brought out, I don't think these numbers have been put up yet though, is that Saturn is a really, really, really neutral-rich environment. You cannot really ignore the presence of neutrals if you're going to be trying to model it magnetohydrodynamically, because they are going to be colliding with and providing local sources for the magnetosphere. So the neutral to ion ratio at Saturn is upwards of 100 to even more right in the peak of the neutral cloud. So I don't put up the equations again, I just tell you that what we're doing again is tracking the dynamics of multiple ion species and electrons. We're self-consistently determining sources from electron impact ionization as well as photoionization. And this is where I think we differ a tiny bit from what Shinja's presented. They showed really nicely their source terms based on where the peak ionization rate was expected, which meant for a very nice symmetric source term around just outside the orbit, peaking just outside the orbit of Enceladus. What we do here, though, is we actually rely on the information in the plasma dynamic model. What are the electrons doing to locally dictate what the ionization rate is going to be everywhere in the model? And that's a very self-consistent way to do it because, as I'll show you in a few moments, those interchange fingers, those interchange instabilities that form from the mass and momentum loading, they drive cold plasma out, they bring warm plasma in. And that warm plasma is, in fact, and I think Jim mentioned it yesterday, but the warm plasma is Fran's missing warm plasma, the warm plasma she needs to get the chemical equilibrium correct. So it's really important, I think, if you want to look at inner magnetospheric dynamics, so anywhere from 3 to 10 Saturn radii, to do it self-consistently because it gives you the local asymmetries and the kind of self-controlled sources and radial interchange that is going to be governing the inner magnetosphere in the system. Since we've already heard about Saturn quite a bit, I'm going to skip through these introduction slides just to remind you there is a massive neutral cloud, which is what we're dynamically coupling to in the model. And we're running this for solstice conditions, as you are familiar with. During southern hemisphere solstice, the attack angle of the solar wind is coming in at about 27 degrees relative to the ecliptic, and that's causing that bowl-shaped structure, which Shinja mentioned in his talk. So I won't spend any time on that. These are some of the preliminary results from the model. You see here, we're plotting the proton pressure. This is total proton pressure, so solar wind protons and ionospheric protons sourced from Saturn. And you see here a really nice standoff distance of the magnetopause. The magnetopause standoff distance varies anywhere from in the model, it varies anywhere from 24 to 28 RS, which is relatively consistent with what Nikahilios and others have seen from the observations. You see this really nice magnetopause formed. You have H plus inside the magnetosphere, H plus in the solar wind, and really nothing happening upstream of the solar wind, of course, as Margie pointed out. It's a nice thing to see with these shock structures. You shouldn't get anything propagating upstream. This is just the side view, again, looking at proton pressure. You see this really nice bowl-shaped structure of the plasma disk, and we can map the magnetic field structures over that. And then I just want to toggle between this and the next slide, which is the water group pressure. So this is water group ions that are freshly sourced from impact ionizations and photoionization with the neutral cloud, as well as charge exchange. And so here you're looking just at water group pressure, and you see again, it's confined to, there's none upstream, because there's no water group ions on the solar wind, not really any. And we see that this is really nicely confined, also maps the plasma disk out quite nicely. And we can compare to lots of different types of observations, looking at the radial extent of water group pressure and temperatures and magnetic pressures in the inner part of the magnetosphere. And we're becoming we believe that by tracking the ionization rates locally based on the local plasma population, that's why we're getting such good agreement with the observations made and the variabilities in local time in the observations made at Saturn's magnetosphere. Just to give you a sense, this is mapping what the water group density, again, newly sourced water group ions versus a kind of collective plot from Anne Pursu in 2009 where she maps out the water group ion density. I have to apologize, I didn't quite realize that this was a log scale up here, so the dynamic range is the same, but this isn't a log scale in color, which is why the colors don't perfectly match. The contours are the same contours though, so just draw your eyes to the contours if the colors are too distracting. So we're really getting very consistently the same thing that she found by going through all the RPWS data and basically creating a static model of what the distribution of water group in the magnetosphere should look like. I won't cover this because Tom did a great job talking about radial transport and interchange, but just as a quick reminder, you have warm injections of warm plasma coming in and that radial outflow of that cold plasma moving out. And that's really important, I think, because, oh, and that's just me being cheesy and drawing the spacecraft flying through it to show you how those injections appear, and those plots from Hill et al. And from Jim Birch's paper and Barry Mock's paper where they first characterized these injections. But again, if you really want to understand the source of plasma, the source of mass in the inner magnetosphere from interactions, from impact ionization, and from charge exchange interactions, we know that it's going to be a locally dependent scenario because we have these injections that are bringing locally warm plasma into the system. So here I'm just showing you an equatorial cut at that water group density. Again, this is not a log scale, it's just a regular scale. And you can see hints to the fact that you have this cold water group material being flung outwards. Those are the interchange instabilities in the model due to that distributed mass and momentum loading. And you can map this all sorts of ways to compare to data. You can compare against the co-rotation lag. You can compare against lots of different scenarios. This is my last slide before my conclusions. So what I want to just show here again, it's a little bit hard to see. I just picked a very simple monochromatic color bar to show you the temperatures. So we show a lot of plots that show the mass interchange, mass being flung out, what look like interchange fingers going out and diffuse injections coming in. But here I want to just draw your attention to the temperature because of course temperature is what's important for local ionization to occur. And this is a very short, it doesn't run for hundreds of hours because that was a really large file to transfer on this internet connection, it turned out. But this is just a couple of hours where you can see again this cold, black is cold, that's the cold material coming out. This red, this brighter red here, those are injections, diffuse plasma, so that's low density plasma from the outer magnetosphere coming in, but at high enough temperatures to really make a local impact on the impact ionization. So to really make a localized enhancement in the impact ionization. This is a self-regulating system. If you create more plasma, more cold plasma, you have more being flung out, then you have very thin channels of hot plasma rushing back in. Those hot channels are where the bulk of the ionization is occurring. So it's not a smoothed out scenario, it really is a local dynamic scenario which allows you to have those interchange instabilities forming. So in conclusion, I just really wanted you to take away two things from this talk. Obviously, the near space environment of planetary bodies contains neutrals. Solving for neutral plasma interactions leads to electrodynamic feedback in places like the ionosphere at Mars, specifically in the dynamo region, and that's actually specifically in the region that MAVEN's deep dips are going to be occurring. So really understanding those feedbacks, the electric fields, the accelerations of plasma in that region is going to be very important to teasing out the details of what should be a really remarkable data set from MAVEN. And that neutral-rich environment of Saturn's inner magnetosphere, you need to self-consistently solve for the neutral plasma interaction if you want to really be able to look at those non-uniform mass and momentum loading feedbacks in the system. And so maybe it doesn't matter if you're just worried about where the magnetopause boundary occurs because MHD is going to give you the right answer there. That's what it does. But if you want to look at the internal dynamics on the shorter time scales, you want to have that dynamic feedback being solved self-consistently. And so there is a little bridge between these two very diverse bodies, and I'll leave it at that. Thanks.
Thank you very much, Carol. Excellent job. Time for a couple questions. Yes, Pat.
I think the crystal magnetic fields at Mars are very exciting, and I think the Hall currents that you're seeing there are quite interesting, but I would imagine the whole structure is going to change depending on its solar zenith angle, because it's going to be part of the whole solar wind ionosphere, you know, and cause a local bump, and that will also create new currents, I would imagine. Yeah. Also, because you will have these structured magnetic fields, you might end up with some open field lines, and one of the things that they saw on Venus and Mars is where those field lines are open is where the largest part of the loss rates are coming from these field lines that leave the surface. And are you going to try to extend your model?
Yes, as soon as we get some funding, we'd be really happy to extend the model. It turns out it's very complicated to model these things with high resolution, but obviously we've actually chosen specifically to use locations that isolate the effects of just the dynamo currents. Obviously, if we put this on the day side versus the night side, not only does it change the draping angle of the solar wind interaction magnetic field, but also the ionosphere in general, because the day side ionosphere at Mars is much different than the night side ionosphere at Mars. So we've investigated kind of local snapshots in time for local times and solar wind draping. But the right way to do it is to put it into a fully global model. And that takes time and effort and a little bit more grant funding than zero.
In your Saturn transport simulations, the excuse me, the azimuthal wave number of your interchange fingers looked like it was maybe 4 or 5 or 6 fingers per 2 pi.
Yeah. Which is a lot different than what you were showing for the RCM.
Exactly. And the question is, do you think that's just a function of grid resolution in the codes?
I've asked you that question so many times every time you present, Tom. Of course, there is going to be some functionality of grid resolution, but what we notice with the simulation is that the longer you let it run, the more consolidated those interchanges become, especially the closer you move into Enceladus. You can almost see it getting smeared out in terms of the way it diffuses once you get in. And I think that's consistent with the fact that we don't observe as many of these interchange instabilities the closer in you get. You see many more of them further out. So I think you're right that we would expect, if I zoomed out, because that I didn't tell you, that white line in the previous slide, that's the orbit of Enceladus. So this is really trying to look very close in. The further out you get, the higher order structure you get and the more interchange fingers you get. But close in, we're seeing at the beginning, when we first start the model, you get a lot, but over time they smear out, so it ends up hitting a fundamental mode that's close to anywhere from 3 to 6.
Well, I thought that was very nice, and I don't know a whole lot about Mars, so forgive this question but I thought it was an interesting approach, actually, in the generalized Ohm's law. Instead of in A to J, you can actually put in the collision terms. And I was wondering if you had estimated what the size of the ion inertial length is relative to the dissipation scale.
I'm sorry, can you say one more time? What the size of?
The ion inertial length relative to the dissipation scale, because if you're really getting decoupling of the ions and the electrons, there should be some scale difference. Otherwise, the dissipation scale will push them back together. So I was just curious if you had estimated that. And the second part is you showed these strong currents coming from the decoupling, right? And I was wondering, do those strong currents actually have any effect then on the ions through the J cross B force?
So I'll answer the second one first because that's actually the easier one to answer. Yes, they affect the ions, but only at altitudes where the ions can be coupled to the magnetic fields. If that collision frequency, if they're in their gyro radius, if that collision frequency is too disruptive, they can't follow the perturbations. But above the dynamo region is where you actually can start to track accelerations in not only the electrons, but the ions due to those perturbation fields, which is why I think it's going to be really important for understanding the velocities and the escape rates of the ions at those regions. Your first question, I wasn't completely sure of how to answer, and we could just talk about it afterwards if you like. But again, it's really the collision frequency, which is a function of altitude, because neutral density is a function of altitude, as is ion density. So yes, the ions will want to respond to the electrons if they're having differential motion, but if it's due to an electric field and magnetic field interaction, they really can't in the dynamo region. They can above it, but in the dynamo region, their paths are being disrupted by the neutral collisions and driven by the neutral winds.